Recall that in R2, it's possible to simplify some integration problems by switching into polar coordinates. In R3, there are two ways to generalize to polar coordinates. We've already discussed the cylindrical coordinate system, but today we're going to talk about a new coordinate system called spherical coordinates. Spherical coordinates have two angles, theta and phi, and one radial coordinate that we're going to call rho. So in spherical coordinates, there is only one length coordinate, and that is the distance from the origin straight out to your point. Now, at the same time, you can project this rho down. That projection down there will have the same angular coordinate theta, and this will be our usual r from polar coordinates. Now, the third coordinate here is the angle from the z-axis down to rho. The z-axis here is sometimes called the pole, so this is called the polar angle. Now, in spherical coordinates, we will always take positive radial values. Theta is called the azimuthal angle, and this one goes from our usual 0 to 2 pi, and the polar angle now goes from 0 to pi. That means it can either point straight up vertically, and its maximum then is all the way straight down vertically. We don't allow for the polar angle to go from vertical back up to vertical. So a point in spherical coordinates is described by rho, theta, and phi. Now, it's possible to connect them back to Cartesian coordinates and also to cylindrical coordinates. If need be, this distance here will be x. Up there, that distance would be y. So as before, we've got that x is r cosine of theta and y is r sine of theta. What we need to do is translate r into these new spherical coordinates. So to help us understand that, we're going to take a look at the side view of this configuration above. What we will see is this radial arm here that has a distance of rho, and then there will be our polar angle phi in there. This distance is r, whereas this vertical distance here is z. And from simple trigonometry, what you're going to see is that r will be rho sine of phi, and z will be rho cosine of phi. And we're going to use these relationships throughout. X will be rho sine phi cos theta in spherical coordinates. Y will be rho sine phi sine theta. And just from above, Z is rho cosine of phi. So this is what you would use if you had spherical coordinates and you wanted to get into Cartesian coordinates. Now, at the same time, we want to be able to go the other way. Now, if you look at that side view from above, what you're going to see is that rho squared is then r squared plus z squared. But r squared from polar coordinates we know is x squared and y squared. So we get rho squared is x squared plus y squared plus z squared, or rho is simply the square root of that quantity. And that's because we are always taking rho to be a positive number. From polar coordinates, we know that the theta value will simply be the inverse tangent of y over x, and phi will simply be the inverse cosine of z over rho. But now we know that rho is given by this square root, x squared plus y squared plus z squared. So these connections right here allow you to convert from x, y, and z into rho, theta, and phi. So for example, if you wanted to convert the point 2 pi over 4 and pi over 3 from spherical coordinates into Cartesian coordinates, we'll have that x is rho sine of phi cosine of theta, which in this case will be 2 times the sine of pi over 3 times the cosine of pi over 4. The sine of pi over 3 is root 3 over 2. Cosine here is 1 over root 2. So this ends up giving us root 3 over 2. Y will be rho sine phi sine theta, which in this particular problem is going to end up giving us exactly the same value. So we'll get a root 3 over 2. And finally, Z will be rho cosine of phi, which in our case will be 2 times the cosine of pi over 3, which will be 2 times a half, which is just 1. So this point becomes root 3 over 2, root 3 over 2, and 1. Now we can also go the other way. So for example, if we are given the point -1, 1, 6 in Cartesian, we could convert this into spherical coordinates. So rho would then be the square root of -1 squared positive 1 squared root 6 squared, which just ends up giving us a root 8. Theta will be the inverse tangent of 1 over negative 1, which is the inverse tangent of negative 1. This means that the angle's either got to be in quadrant 2 or quadrant 4. If we're going to have positive theta values, then we're going to pick the quadrant 2 answer. So theta will then be 3 pi over 4. And phi will then be the inverse cosine of z over rho, which in our particular case will be the inverse cosine of root 6 over root 8, inverse cosine of root 3 over 4, which is inverse cosine of root 3 over 2. This asks a question: what angle do I need to take the cosine of to get root 3 over 2? The answer will be pi over 6. So the point here becomes root 8, 3 pi over 4, and pi over 6 in spherical coordinates. The real advantage of using spherical coordinates is in understanding its coordinate surfaces. Now remember that coordinate surfaces mean that one of the variables is fixed or constant and the other two are free. If rho is a constant here, let's say it's some rho naught, and then theta and phi are free, you can imagine as if you're sitting on a chair and you've held your arm out fixed, and your arm is at some length, rho naught, and now the angle below is free to rotate. This theta is free to rotate. So this is like being on a chair that can spin around, and then simultaneously you can lift your arm up and down. And when you do that, you will end up tracing out a sphere. If your theta value is fixed at some angle, and rho and phi are free, what ends up happening is that you are now rotating at some constant angle here, and then your radial value is free to go out as far as you'd like, and your angular value is also free to go up and down as far as you'd like, this value in here. So what this ends up generating is an infinite plane, and it will be vertical at some sort of angle. And finally, if you held your angle fixed at some value and you let rho and theta be free, once again, you can imagine being on a chair that can rotate around, and now you're setting your angle fixed at some phi naught, and your radial value is free to extend, and then your angular value is free to rotate around. So what this does is it produces a cone. For comparison's sake, if you were to write a cone in Cartesian coordinates, you'd have to have some sort of scaling constant factor to ensure the right height and radius. The equation of a cone in cylindrical coordinates, it would be r times the cotangent of this angle here. Just setting phi to be a constant makes it very, very easy to describe a cone. So for example, if you wanted an ice cream cone you can think of as spherical cap. It has this cone on the bottom. And let's say that this is now a radius of 1. If we knew the angle of the cone here, let's say it would be pi over 4. The description of the cone would be radial values going from 0 to 1, angular values being filled out from 0 to 2 pi in this azimuth angle. Polar angle would then simply go from 0 to pi over 4. This is a very simple way to describe this cone, which would be quite challenging in Cartesian.